So recall, blood pressure is measured as two ratios, the ratio between the systolic and the diastolic pressure. The systolic pressure is the maximum pressure it takes to open up that aortic valve, to push all the blood out of the left ventricle. It's being purified with oxygen coming in from the pulmonary veins and then pushed into the aorta so it can be then sent out to all the arteries of the body. After that's done and the heart relaxes, then we have the pressure in what's called the diastolic phase. All right. So if we slowly go back to our model that we've come up with, we've been able to use a couple of relationships, especially for compliance and resistance, to come up with a differential equation that describes this change in the pressure, the arterial pressure, with the initial condition that at time zero, you essentially have the systolic pressure. Same thing at the end of the heartbeat, which is given by the time capital T, that would be the other pressure, which is the diastolic pressure. So this is actually something I hadn't mentioned before. So we're looking at blood pressure as the relationship between those two. Right? So the solution to the differential equation of how that pressure changes through time is given by this particular solution here, the exponential form solved by that very simple linear differential equation. It's very separable, no problem. And again, you see that the initial condition is given by the systolic pressure. What we'd like to do is use this mathematical model to estimate physiological parameters for compliance and resistance. In other words, to get an idea of how that changes based on measurable quantities. It's very difficult to intrusively go into the bloodstream or go into the body to figure out how stretchable or how resistant the blood flow is. So this mathematical model can actually do that based on certain quantities that would be easily measurable. First of all, the heart rate, or in this case, the pulse, which would be 1 over T, which would be very easy to measure. With the Doppler sonogram, you can actually measure the cardiac output Q. And then, of course, using our blood pressure sphygmomanometers, you can get the systolic and diastolic pressures, P-sys and PDIA. All right. So let's see, how can you model the compliance and resistance with this differential equation? All right. So what we know is that if we go back to our stroke volume, V, it could be represented as the difference between the stroke volume during the systolic phase minus the stroke volume during the diastolic phase, which based on the definition of the volume in terms of compliance would be represented as C sub A times your systolic pressure minus CA compliance times the diastolic pressure. And to keep in mind, this is the same thing from our model of our arterial pressure at T0, PA of 0, and this one is the same thing as if we're looking at the end of the heartbeat at PA of T. So, therefore, since we know that the stroke volume V can be thought of as cardiac output times the time period T, right? It's easy to show that the compliance could be measured as QT over the difference there, which would be PSYS minus PDIA. So here's one model of how to estimate someone's compliance, ability to stretch the blood vessels based on those measurable quantities and using the mathematical model. For resistance, you can use the fact that we know that the diastolic pressure is the same thing as PA of T. Use the solution to the differential equation, right, to get that this is E, and we'd actually have capital T, not just little t up there, capital T over the product compliance time resistance, right? So, having done that, solve for the resistance there, and what you would come up with is that the resistance would have to be T again, the length of the heartbeat, divided by the compliance times the natural log of your systolic pressure minus the natural log of your diastolic pressure. So here we are. Two ways of using our mathematical model produced from a very simple linear differential equation representing arterial blood pressure to estimate two very important factors that can be used to determine hypertension and other sorts of diseases in humans. So just as a usage of this model, these two factors I hear that we have in these two boxes, what I thought I'd do is show you the difference between a normal person, we'll represent that as NP, versus an athlete. Say, since we just had the Olympics, maybe how that would be different in terms of the data and what these two models would produce. All right? So let's look at that. We'll make two columns. We'll just look at how a normal person and an athlete would vary according to these parameters over here. So we're just making a little chart here. All right? And in the chart, we'll measure 1 over the pulse, 1 over T. Look at the cardiac output, the systolic pressure, and the diastolic pressure. All right. So typically, a normal person, it'd be about 70 beats per minute. Athlete might be a little bit lower, 60 beats per minute. Again, at rest. Typical normal person cardiac output, we'll just say about 5.6 liters per minute. Athlete, a little bit more than that, 6 liters per minute. Okay. In terms of systolic, typical values you would see 120 millimeter mercury. For a normal person, about the same for the athlete. Mercury's 80 on the diastolic. And this might be a little bit lower for the athlete. They can get that pressure down just a little bit more. Okay. So what you then do is use this model of compliance and resistance with these parameters that are easily measurable, plug them in, and let's compute the differences and see what we get. So what we're going to look at is, let's now see with this table of data what the difference would be between the normal person and the athlete with regard to a couple of things. We're going to get CA, and we're going to look at RS. Okay? Compliance and the resistance. Well, it turns out for a normal person, it'd be about 0.002. And for the athlete, it would be about 0.00, slightly larger, add a few more significant figures. And the unit would be liters per millimeter mercury. Okay? So it's only slightly larger for an athlete. Turns out the bigger difference is here in the resistance. Remember, the resistance is the ability of the blood to flow. For a normal person, about 17.6. Athlete, be lower, 15.96. And this would be millimeter mercuries per liter per minute. So an athlete will typically have a much lower blood resistance. In other words, the blood would flow a lot more efficiently, faster perhaps, for an athlete than it would for a normal person. So I hope you can see the advantages of looking at differential equations from, say, more biomedical application, how important it can be to build mathematical models to allow people to compare performances and very important properties related to disease management and control.